Alrighty, so sorry for the delay. Dom had some technical difficulties, and so I stepped in and I recorded this, and then I realized that my microphone was off the entire time. So here we go for a re-record on this. And so anyway, today I figured we were just going to go over some more triple integral questions from the textbook, ones that are a little bit different from the ones on the WebAssign. So this will give you a little bit of a different perspective on this. And so yeah, the first one I wanted to take a look at was 15.6, number 10. And so it starts off, you're asked to do the triple integral of e to the z over y. And this region E is given by points x, y, z in space, such that y is between 0 and 1, x is between y and 1, and z is between 0 and xy. Okay, and so for this, it doesn't really give it to us as a triple integral, but it is pretty much giving us the bounds. We just have to make sure that our bounds, the way we set it up, is going to give us a number as an answer. So for example, if I did dz, dy, dx, that wouldn't be any good because the x bounds, notice, have a y in them. So remember our rule, the answer has to be a number, which means the outermost bounds have to be numbers. The middle can only contain the outer variable, and then the inner can contain the middle or the outer variable. And so anyway, if we just do it in the order that's basically given to us, if we put y on the outside, x in the middle, and z on the inside, then this follows all of our rules as far as the outer variable, outer bounds are numbers, the middle bounds have the outer variable only, and then the inner bounds are allowed to have the middle and the outer. So anyway, this looks good. And so therefore the first step to solving this would be our z anti-partial derivative, which is going to be y e to the z over y from z equals 0 to z equals xy. So again, hopefully you've been practicing these a fair bit. You know, when I look at e to the z over y dz, I'm thinking, okay, that's basically, I'm trying to do like the antiderivative of e to the x over 2. Right? Because for the purposes of the z antiderivative, you're pretending that y is a number. You're also pretending x is a number, but there's no x, so that doesn't really amount to anything. But yeah, back in Calc 2, if you wanted to do the antiderivative of e to the x over 2, you would get 2 e to the x over 2. So similarly, the anti-partial derivative with respect to z of e to the z over y is y e to the z over y. And we still have our x and y layers here. So 0 to 1, y to 1. Okay, and so then when z is xy, you have xy over y. So this is what, y e to the x. And then when z is 0, well, e to the 0 is 1. So we get y e to the x minus y dx dy, and so therefore our x antiderivative is y e to the x minus xy, evaluated between x equals y and x equals 1, and so therefore we get, well, y e to the y minus y squared, and then minus, oh, sorry, I did the bottom bound first. So when x is 1, we get y e minus y. So y times e minus 1 is what we get when x is 1. And then when x is y, we're going to get minus y e to the y, and then minus negative y squared. I'm being careful with the minus signs. But anyway, that's what we get there. And so then at that stage, I guess technically you're going to need integration by parts. For y e to the y, you're going to do u equals y, dv is e to the y, dy, du is dy, and v is e to the y. So that after you do uv minus the integral of v du, you'll get y squared over 2 times e minus 1 minus y e to the y minus e to the y is your, after you do the uv, minus integral v du. And then antiderivative of y squared, of course, is plus y cubed over 3 between 0 and 1. And so I plug in at this stage. It's nothing too exciting. This is e minus 1 all over 2 minus, well, when y is 1, we're going to get e minus e, and then plus a third. And then when y is 0, be careful, you're going to have a minus 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 1, because e to the 0 is 1. So e over 2 minus a half, and then minus 2/3. A half minus 2/3. Well, sorry, minus a half minus 2/3 is going to be minus 7/6, and that sounds familiar. Remember, I recorded this a few minutes ago, well, an hour ago or so, and had the microphone off. So let me just make sure I didn't make any small mistakes. Yeah, e over 2 minus 7/6 looks good. Okay, and so like I've said before, I don't worry about parts for integration. Obviously, this is pretty standard situation for integration by parts, so hopefully all of you remember this from 141, but we're not going to really make you do that for a quiz or a test. So anyway, that's that one. What's the next one I wanted to take a look at? Number 12. So 15.6, number 12. We're supposed to do the triple integral of sine y dv, where e is below z equals x and above the triangular region with vertices 0, 0, 0, pi, 0, 0, and 0, pi, 0. So anyway, I found I'm much better at drawing planes where they have x, y, and z intercepts that none of which, well, that they all make sense. So for example, earlier this week, we've saw the shortcut that if your plane equation is like x over a plus y over b plus z over c equals 1, then the x-intercept is a, the y-intercept is b, and the z-intercept is c. And so the piece of the plane in the first octant, for example, if a, b, and c are all positive, looks something like that. But anyway, I found that something like the plane z equals x, I'm not nearly as good at drawing. I guess the idea is that if z is x, it's going to look something like this. And then if you're going to draw pieces like this, the cross section at any y value is that line z equals x. So the plane sort of touches the entire y-axis. And for me, that makes it a little bit harder to draw. So I'm not going to try and draw it like that. Instead, I'll try to draw it without the axes just to convince you that this is actually a solid tetrahedron, sort of like what we've been talking about. So yeah, this picture over here is not good for z equals x. Since z equals x, like I said, touches, it intersects the entire y-axis, right? Okay. So how's this going to end up looking? So I guess this triangular region, we can sort of draw that this 0, 0, 0, pi 0, 0, and 0, pi 0, those are all in the xy plane, right? Because the z-coordinate is 0. So if I draw that, that's sort of here. So pi 0, 0. If this is my x-axis, this is my y-axis, I have 0, pi 0. And so it says above that triangular region. So it sounds like the shadow in the xy plane is this triangle right here. And so I'm going to need it later. I can figure out the equation of that top curve, it's y equals pi minus x. Okay, so anyway, it sounds like that's our base of this solid tetrahedron that I have. How's this going to look? If this is pi 0, 0, that's there. This is 0, 0, 0. This is 0, pi 0. And so the plane z equals x is sort of coming out of this y-axis here, and means that, let's see if I can find it. Basically, oh no, that's not right. There we go. We have this tetrahedron. The bottom face is the piece of the do I like this perspective? Yeah, I think it's rough, but yeah. Let me think about how I might draw this a little more clearly. So I have my bottom triangle in the xy plane. I have this point here. So that's going to be pi 0 pi. So it's directly above pi 0 0. And then I, of course, have my origin, and I have my point 0 pi 0. So then I have that triangle, which lives in the xz plane. And then I have which triangle? So this triangle that has pi 0 pi, 0 0 0, and 0 pi 0. And so yeah, the tricky thing is that it sounds like the bottom surface is z equals 0, and then the top surface is the plane z equals x. Which, when you read this thing, you're always on the lookout, remember, for the inner variables. You're looking for the, if it's dz on the inside, you're going to want to look and find the bottom and top surfaces. So when I see z equals x, I'm like, okay, it's z in terms of x and y, so that's probably going to be either my bottom or my top surface. But it's going to be the top surface because it says it's below that, and then it says above the triangular region. As soon as I see these 3 zeros, I know that that lives in the xy plane, so that's my bottom surface. And so anyway, putting it all together, it looks like my innermost z bounds are 0 to x. And of course, I have sine y dz, and then my x and y bounds are 0 to 1, 0 to pi minus x. So again, this xy shadow that we drew, it's not a rectangle, so therefore we have to have variables somewhere, and we have the top curve y is pi minus x. Okay. And so that's dz dy dx. We can go ahead and get started. So the z antiderivative is, of course, z sine y between 0 and x, dy dx. I guess I should remind us that these are values for z equals 0 to z equals x. So I'm left with 0 to 1, 0 to pi minus x, x sine y, dy dx, whose antiderivative with respect to y is minus x cosine y between y equals 0, y equals pi minus x. And so you end up getting 0 to 1 minus x cosine of pi minus x. And then if y is 0, cosine of 0 is 1, minus minus, and so I'm getting plus an x. And so with this, you can leave it as is. I guess I'll do it as u equals minus x Yeah, so you actually need integration by parts for this one again. But again, it's a fairly standard integration by parts. You end up getting, if u is minus x and dv is cosine of pi minus x, that du is minus dx and v is minus sine of pi minus x. And so we're left with, for this first term, you'd get minus x, well, uv is x sine pi minus x, and then minus v du. So minus v du has 3 minus signs, so it's minus the integral of sine pi minus x, whose antiderivative is, well, the antiderivative of sine is minus cosine, but then we have another minus because of the chain rule. You're going to have minus cosine pi minus x. So anyway, our antiderivative is x sine pi minus x minus, so yeah, minus cosine of pi minus x, and then plus, of course, x squared over 2 between 0 and 1. And this is not 1. Sorry about that. This got a little ahead of myself. Of course, x goes from 0 to pi. So yeah, x goes from 0 to pi, 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 pi. Okay, so pi sine of 0, well, sine of 0 is 0. Cosine of 0 is 1, so I get minus 1 plus pi squared over 2. And then when x is 0, the first term's gone, the third term's gone, but then cosine of pi is negative 1. So minus cosine of pi is another minus 1, so pi squared over 2 minus 2, and that is familiar as well. And so again, focus more on the setup of parsing the idea that we're below the plane z equals x, we're above the plane z equals 0, and then it sounds like our shadow is that triangle with 0, 0, 0, pi 0, 0, and 0, pi 0. Okay. So the next one, we're going to look at number 16. So 15.6, 16. We're supposed to do the triple integral of xz, where E is the solid tetrahedron with vertices 0, 0, 0, 1, 0, 1, 0, 1, 1, and 0, 0, 1. And so again, it's kind of similar to one of the tetrahedron examples we went over on Tuesday, I believe. Maybe it was Monday, actually. But then it's a little bit like the one we just looked at, but a little bit different. So let's see if we can imagine drawing this. So we have 0, 0, 0. We have 0, 0, 1, which of course is just directly above it. I could put my x and my y axes like this, so y and x. And then I have 1, 0, 1, which is going to be here above the x-axis, and then 0, 1, 1, which is here on the y-axis. So it sounds like we have this horizontal top triangle, and then we have this situation going on. So it sounds like this is our solid region. We're stopping at this plane z equals 1. Because if I look at these 3 points, well, they have z coordinate equal to 1. So certainly they live on the plane z equals 1, but then remember 3 points determine a plane, so that has to be the top surface here. And then the bottom surface is, if you put it together, it's the plane containing 1, 0, 1. Well, I'll write it as 0, 0, 0, 1, 0, 1, and 0, 1, 1. So we have to find the equation of that plane. Well, we know that the displacement vector from the origin to 1, 0, 1, which is just the vector 1, 0, 1, and from the origin to 0, 1, 1, point along the plane that we're looking for. So this is just a standard question from way back in chapter 12. Remember the equation of a plane containing 3 points. So therefore their cross product, which would be -1, -1, 1, is along the plane, or sorry, not along, but perpendicular to the plane. And so that's what you're going to want to use as your normal vector. And I could use the fact that the origin is on this thing, so putting it all together, it's going to be -x minus y plus z equals 0. And so the equation of the bottom surface, z in terms of x and y, is z equals x plus y. And so that's our innermost z bounds, x plus y to 1, because the bottom surface was z equals x plus y, the top surface is z equals 1. And then I have my integrand. And then as far as dy and dx go, I have, it's pretty much the same triangle we had in the previous problem, except it doesn't have pi as its intercepts. It has 1 as its intercepts. So when you think about this shadow in the xy plane, it's the triangle directly below that horizontal triangle in z equals 1. And so we see it's not a rectangle. You have to figure out that the top curve is y equals 1 minus x. The bottom curve is y equals 0. And then this happens for x between 0 and 1. So go ahead and pause that here. Make sure you understand this is sort of the most important part. This turns out to be a pretty tedious calculation. We probably won't have you do such a tedious calculation on the exam or on a quiz, but we might ask you to set up the bounds for something like this, so make sure you understand. But yeah, let's go through it. Like I said, it's just tedious. It's not even difficult at all. The z antiderivative, of course, is xz squared over 2. And so when I plug in and subtract, when z is 1, I'm going to put this 1/2 out front. So when z is 1, I just get x over 2. But then when z is x plus y, I'm going to subtract x times, well, z squared is x squared plus 2xy plus y squared when z is x plus y. And so then my y antiderivative is xy minus x cubed y minus x squared y squared minus x over 3 y cubed. So I sort of, in my head, distributed that x to each term and then took the y antiderivative. So minus x cubed has y antiderivative minus x cubed y, minus 2x squared y has antiderivative minus x squared y squared with respect to y, and so on and so forth. And so then plugging this in, this is where it gets really tedious, but okay, I have x minus x squared minus x cubed plus x to the 4th minus x squared times 1 minus 2x plus x squared minus x over 3 times 1 minus 3x plus 3x squared minus x cubed. So there's some examples where you don't have to multiply all this stuff out, but for this, it turns out you're going to have to. And then I'm going to do the distributing and anti-differentiating in the same step. Again, if you have to write out another step, that's totally fine. X squared over 2 minus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5. Then minus x cubed over 3 plus 2x to the 4th over 4 minus x to the 5th over 5 is our next few terms. I did the distributing and the anti-differentiating at the same time, but I was careful. And then this will be minus x squared over 6 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 15. So again, none of this is difficult. It's just Calc 1 style stuff. And so we get 1/2 times 1/2 minus 1/3 minus 1/4 plus 1/5 minus 1/3 plus 1/2 minus 1/5 minus 1/6 plus 1/3 minus 1/4 plus 1/15. So 5th minus 1/5 minus 1/3 plus 1/3. What else do we got? 1/2 minus 1/4 minus 1/4, that's 0. So 1/2 minus 1/3 is 1/6, minus 1/6 is 0. So it looks like we get 1/30, which, yep, that is correct. So again, the last few steps, don't worry about. That's a lot more tedious than something we would make you do. So what next? I think the next one I wanted to do was number 22 out of the book. So it says find the volume enclosed by the cylinder x squared plus z squared equals 4, and the planes x equals -1 and, oh no, sorry, y equals -1 and y plus z equals 4. So the cylinder that we're dealing with is around the y-axis, of course. And so y equals -1 is this plane over here that's perpendicular to the y-axis. And then y plus z equals 4 is sort of a diagonal plane. All right, you could just think about the line, what y plus z equals 4 looks like in the YZ plane, and then all the cross sections are, I guess I should keep my perspective straight. All the cross sections perpendicular to the x-axis are that same line. So I have this piece of it, and this piece, and so on and so forth. So what ends up happening is you get this cylinder that's sort of cut off at an angle like that. So this solid region here is what we're looking at. And so you could do top and bottom surfaces, but you'd have to split it up. The top bottom needs to be split, because notice sometimes the top surface is part of the cylinder, and other times the top surface is the plane y plus z equals 4. So for certain y values, you start and stop on the cylinder. For other y values, you start on the cylinder and stop at the plane, but we don't want to do that. So top bottom needs to be split, but left right surfaces don't, because it looks like the left surface is always y equals -1, and the right surface is always y plus z equals 4. So basically, what that means is that we're going to want to put dy on the inside. Okay, so remember the volume of E, that's when we do a boring triple integral of the boring constant integrand f equals 1. And so we're just going to integrate dy. And so y starts at -1 and stops at 4 minus z. Right? So you have to take this surface. If we're putting dy on the inside, you have to solve for y in terms of x and z, which, okay, not too much trouble on this one. And then I showed you on Tuesday that you don't have to write down the x and z bounds for this sort of thing. It'd be a mess, right? Because you'd have to say that, you know, z starts at minus square root of 4 minus x squared and goes to plus square root of 4 minus x squared. And as far as integrating that, you know, you're playing with fire as far as maybe you're going to need a trig substitution, and we don't want to do that. So we are going to want to switch to polar coordinates eventually. So the first thing we'll talk about next week is that there's something called cylindrical coordinates that allows you to do that on the level of the triple integral. But for today, and what I showed you on Tuesday, we're just going to do this first dy step. So when I integrate with respect to y, I get y. I plug in and subtract, and I'm going to get 5 minus z. And so at this stage, it's up to you. That the long way to do it would be to switch to polar coordinates. And so again, we usually do x and y switch into polar, but these integration variables, or dummy variables as they're sometimes called, who cares what they're named, right? This answer ends up being a number, so who cares if it's an xy versus a xz double integral? So I could, just like how with regular polar I switch x and y into polar, I could switch x and z into polar, and it works the same way. However, the faster way to do this is to realize that this region in the xz plane over which I'm integrating is symmetric over the x-axis. And this term z is odd with respect to z, so intuitively the contribution on the top half is canceled by the opposite z value on the bottom. That this term minus z, it's negative when z is positive, it's positive when z is negative, so the contribution of minus z works against itself on the two upper and lower parts of this disk. And so anyway, you end up just getting the double integral of 5 over this disk of radius 2. And guess what? I know this area. So this is using some of the tricks I talked about at the very beginning of this Monday's lecture. So week 8 or week 2, lecture 1. But yeah, 5 times the area of the disk, which is 5 times pi 2 squared, so 20 pi. And of course, you get the same thing if you actually do all that integration, but remember, be on the lookout for symmetry shortcuts. It could save you a fair bit of time. Okay, and then so the last one I wanted to show you for today was number 30, which asks, here's some triple integral. It doesn't tell you what f is, so f is just the density function. Remember, usually you want to think of triple integrals as calculating the mass of a solid object, where f is the density that changes throughout the object. And E is bounded by y squared plus z squared equals 9, x equals 2, x equals minus 2. What the? That was downright frightening. What the hell was that? That was scary. I don't know. Maybe Siri thought I wanted to play some music. Anyway, back to the math. It says, okay, this is our solid region. Set it up in all 6 orders. And so this will be good practice. So I showed you some of this type of thing on Tuesday, so the second lecture of this week, where you were able to take care of it by just looking at you didn't really have to think about the 3D picture. You could think about it on the level of the rules for which variables are allowed to appear where. Instead, today I'll show you this, where it ends up being not so bad to actually think about the 3D picture. So for this example, we start to think about it. We have our cylinder, and it's around the x-axis, right? So this is our x-axis. And then I guess we would have y going into the page and z going up. And so whether we put x on the inside, y on the inside, or z on the inside determines which surfaces we're thinking of to give us our innermost bounds. So let me scooch that down here. So if dx is inside, then we're thinking left and right surfaces from this perspective. Okay, so that would be, so here's our solid region. Our left and right surfaces, we would be thinking like this, right? What's the left boundary? What's the right boundary? For dz on the inside, then you're thinking top and bottom surfaces. So we have our same set of points that we're looking at. And we're saying, okay, where are we starting? Where are we stopping as far as going straight up and straight down? And then finally, for dy on the inside, from this perspective, you'd be thinking back and front surfaces. So the back and the front surfaces. And so we see that the left and right are the planes that we're given. Whereas for the top and bottom, it's the 2 halves of the cylinder that you get when you solve for z in terms of y. So the top half of the cylinder has equation z is the plus square root of 9 minus y squared. And the bottom of the cylinder has equation z equals minus square root of 9 minus y squared. So that's the bottom. This is the top. This, of course, is the left. This is the right. And then the front and back is essentially what you would get for solving for y in terms of z on the cylinder. So the back surface would be, from this perspective, that's the positive y. That's when y is the square root of 9 minus z squared. And then the front is when y is minus the square root of 9 minus z squared. And so then the other thing that changes is the shadow, the d for the outer bounds and the middle bounds. It's the shadow in the yz plane of our solid cylinder, which for dx on the inside is going to be a disk. So we could draw that the shadow in the yz plane is the disk of radius 3. Whereas we get rectangles as the shadow in these cases. So let's see if I could draw that. The widest part of this cylinder, of course, is in the middle. And so the XY shadow, yeah, just imagine taking a cylinder. When you have the shadow this way, you get a disk as the shadow. But if you look at your cylinder like this, it looks like a rectangle, right? You can't tell the difference between this and a rectangle from this perspective. So anyway, yeah, our shadow in the XY plane is, I guess, yeah, a rectangle that's goes up to y equals 3, goes up to x equals 2, and then is symmetric over both axes. And our shadow here is this shadow in the xz plane, which again is a rectangle. That the xz shadow is our 3x2 rectangle. Okay, and so I'll just do these out of order. We're down here, so if y is on the inside, we said y starts at minus square root of 9 minus z squared and goes to plus. And then if I do dz dx, it would be minus 3 to 3 minus 2 to 2 for my rectangle shadow. I could also switch that to be minus 3 to 3 minus 2 to 2. Same thing, minus square root to plus square root. And then I get the same kind of thing for dz inside. It would be minus square root 9 minus y squared to square root 9 minus y squared. And then I could do x on the outside, z in the middle. Sorry, y in the middle. So f dz dy dx. Or I could do minus 3 to 3, minus 2 to 2, minus square root 9 minus y squared to square root 9 minus y squared f dz dx dy. But then I think probably the best way to do this is with dx on the inside. And then you could, after you do the x integration, switch to polar, but you know the instructions say to do it for all 6 orders. So if we put, say, dz in the middle of dy, then z starts at minus the square root of 9 minus y squared. It goes to plus square root of 9 minus y squared. And then finally, if I put dy on the middle, I'd have y starts at minus the square root of 9 minus z squared to plus the square root of 9 minus z squared. And then x again goes from minus 2 to 2, f dx dy dz. Basically, depending on how you do this, if you do the top-bottom slicing for the yz disk, then you solve for y in terms of x and z. Whereas if you do the left-right slicing, you'd have that y starts at minus the square root of 9 minus z squared it stops at plus the square root of 9 minus z squared. So anyway, that's how that works. So yeah, I think on the homework question, it's more similar to what I was talking about on Tuesday, where you can get away with not really thinking about it in 3D. But I think this was a good example too, to reiterate that, okay, you have your left and right for dx on the inside, you have your top and bottom if you want to put dz on the inside, and you have your front and back if you want to put dy on the inside. So anyway, that's about all I had planned for today. So 2:30 people, good luck on the exam. And 2:32, remember you got another week before your midterm. So anyway, have a good weekend, and I'll see you later.